Hey there, this is a quick demo video for my VLMT Vision Language Model Tuner project. The idea is that through a few convenient GUIs, we can easily go from data labeling to a trained LoRA model that will be tuned well to your specific application. Let's start with the data labeling. So the first thing we want to do is load a folder of images that we want to use for our project. This particular example here is identifying and localizing raspberries, maybe as a quick proof of concept for a fruit picking robot or something like that. We're going to come up with a prompt and we're going to ask the VLM to output a particular format for raspberries identified within a coarse grid and to count how many are within the grid squares. The format we'll train is something that can easily translate into a JSON or something else fairly standardized. We can get started by asking the AI to generate an initial response. You'll see it does alright with the formatting, but gives the completely wrong answer. A quick note, this project is based on the model Qwen2 VL7B Instruct, which is something I was able to set up to run locally on a machine with 16 gigabytes of VRAM. The process and GUI tools are transferable to other models, of course. Now, let's look into how labeling is actually done. I wanted to come up with something that would make it easy for a human labeler to breeze through examples with as little typing as possible. And the solution here was a grid layout that links mouse clicks to generated text in the appropriate format, as you see. Another neat feature is that if you double-click a grid, it increases the object count in that grid. So really, there's no typing. This UI, it's a little bit gaming inspired, so the idea is that quick mouse clicks get the job done. There's some caveats to this sort of labeling. You have to decide what to do with overlap, for example. If the raspberry spills over into multiple grids, do you just pick the main grid where most of the raspberry is, or do you select multiple? Really, it's up to you. I'll breeze through a few more examples quickly. I have a 0 results or none found key phrase that I paste in when there's no objects present. So aside from clicking, I just hit Control B once in a while. If you see black padding, that's because I made a tool to augment my image dataset with random position shifts, image flips, lighting, and contrast changes. You can see this process is actually pretty quick. I got through about 550 examples in just under 90 minutes. Next, let's look at the fine-tuning program. So there's a few panels here. We're going to load our dataset that we just labeled. The previous program saves all your responses in an appropriate JSON format. Then we're going to specify the output directory for our fine-tuned adapter model, and model parameters such as learning rate, batch size, gradient accumulation steps, which is useful for those of us with limited VRAM that want to simulate like a virtual batch. Epochs, evaluation every X steps, and also what subset of N samples from the test dataset do we want to look at, because usually a small snapshot is enough for that purpose. For the LoRA target, we use only the text LLM layers, or we can include the projection from the vision tower, which seems to be helpful for this type of task. LoRa R and Alpha are standard for LoRa model, and Qwen2 VL lets you specify the image pixels to be used for constructing image features, so we can set that max pixels parameter, and we can trade off size and performance. Now there's a training log, which will show you what's running in the background. And something I always wanted was this inference preview, where every so often when we do an eval check, let's just take a random test sample and see how the current model actually does against the correct labeled answer. So we can see performance improvements as it trains, but we can also stop and restart if the process is not going well. So I thought this could definitely save a lot of time, plus it's pretty cool to see the model's performance evolve over time. Training progress has your standard graphs showing training and testing loss throughout. So with all that out of the way, let's hit start training. The log will give you some diagnostics, errors if you run into them, stats on your GPU, and expected VRAM usage, which can be useful when you're playing around with the parameters. By the way, you'll see a dynamic learning rate. That's because by default we have a few warm-up steps, followed by cosine decay, which tends to give pretty stable training for LoRA models. So this is sped up a bit, but you see that you see every bit working as described earlier. You got the loss curves, the inference previews, and you can see the model answer getting better and better compared to the correct labeled answer. You generally don't need more than a single epoch to get the full performance. Now let's open up the inference testing program to get a view of how our model really does. Again, similar panels and interface. We're going to load a data set. LoRA adapter directory is the model we just trained, and the base model we need to point to is, of course, Qwen2VL. We'll want to specify a consistent max image pixels for the vision tower, as we had in training. And we have generation parameters for inference like temperature, top P, and our max tokens. Now, the results window uses the number of buckets parameter to create a histogram of losses across your entire data set. You'll see this in a moment. The inference preview is very similar to before, but now it gives us the correct labeled answer, the base model answer, i.e. the answer without any training, and your trained LoRA model's answer. This is useful because you get to see exactly how impactful the fine-tuned model training really is. But you get to also debug specific examples of where the model does well or doesn't do well. This can help you refine your application. Maybe you realize you need to edit the prompt for a few edge cases, throw in some examples, create your labels in a different way, or just see what the limitations and success cases look like for your project. When we hit Start Inference, we run the base model as well as the LoRA model across every single example. We can typically load all of this into VRAM because the LoRA model only adds a few hundred megabytes of extra parameters. Afterwards, in the dataset selection panel, we'll be able to click on and inspect any specific example. So I sped this up a fair bit, and you can see from the final results that essentially over 350 examples have practically no error. And then we have this drop off towards worse examples, which there are not that many, but they're all there and we can investigate them. So let's look into some of those. The losses are now present next to the image names in the top left panel, and those that are highlighted light red are examples that fall within the bottom 10% of performance or the 90th percentile of errors, however you want to look at it. Therefore, those are usually good candidates for debugging and performance monitoring. We can see from practically any example that the base model is not able to give us anything close to what we want, as localization and counting are pretty difficult for these VLM models. Looking at the LoRA model answers, we see pretty good coverage overall. The main differences when you zoom in on it tend to be off by one row or column numbers, and a lot of this will be just due to how we labeled and handled overlap. You know, that issue of the Raspberry appearing in two different grid spots. So let's look at a more poor example with a higher loss value. And what we see here is that we're missing an entire line of text, which will induce a higher error in token space for sure. But for practical application purposes, we see that the model just decided to not count one of the adjacent grids, possibly due to overlap. So we're missing a bunch of characters and tokens, but conceptually, this model answer actually makes a lot of sense, and it's pretty close to the ground truth. We'll open and look at another one, and we see a pretty similar story. Again, the base model doesn't really know what's going on and gives close to random guesses, though at least it follows the format decently. We can go through a few more quickly. Honestly, I'm pretty happy with how this turned out, though. The main thing that our network seems to have learned is to identify vision features with raspberries and locations of those vision features with a 1 through 8 grid of rows and columns, which is exactly what we wanted. Now, as a quick aside, for this use case, I recognize that a dedicated vision model or CNN would have been more appropriate, but for demonstrating VLM fine-tuning and constructing a custom output based on text, I think this demonstrates the usage potential pretty well and gets the point across. It also shows the limitations of a base VLM model, but also how easily we can improve on them for something specific. Clearly, Qwen2VL understands what raspberries are, as do most vision language models, but it couldn't count them or tell us where they were in the image. However, with a small labeled dataset and this LoRA fine-tuning, it's like we're building upon that core base intelligence, and we make something work specifically pretty well for what we want. Anyways, that's all. Thanks for watching, and feel free to ask any questions. Thank you.